All right, here we go. We're talking about simple harmonic motion. I figure a good place to start with this would be just defining what I mean when I say simple harmonic motion. My definition of this term goes like this. Simple harmonic motion is any object which moves between two positions repeatedly without anything changing. So any object which moves between two positions repeatedly without anything changing. And what I mean when I say without anything changing, I mean like on those repeated motions, the distance it moves isn't changing, the amount of acceleration or speed that the object has, all of that stays the exact same. That's what makes it simple, right? That's what makes it that simple harmonic motion. Another term for all of this is oscillating. That is a term that when you get to the AP exam, the moment you see that word, I want you to immediately switch into simple harmonic motion. Because really, simple harmonic motion and oscillation, they're synonyms. They mean the same thing. It just means something moving back and forth over and over and over again. Okay, so the first thing we're going to do when it comes to simple harmonic motion is we're going to look at some motion graphs. Okay, a little bit of a blast from the past. When it comes to topics here, as we talked about this all the way back in first semester. But if we were to look at the motion graph for, let's say, a pendulum swinging back and forth, if we were to mark the pendulum's position on a position versus time graph, it would look something like this. Make its way away from the x-axis and then come back and pass through. Something like that. Should be, this should have the same height as over here, but I'm just not good at drawing. But this is what it looks like. It's a sine graph. You've seen this in math class. The next thing we're going to look at here is velocity versus time. If this is our position versus time graph up here, well then let's see. We start with a high positive slope right there. So that means we have a high positive velocity. And that slope on our position versus time graph slowly decreases until it's about 0 at this point. And then it increases to its maximum around here. And it starts decreasing to a minimum here, increasing to a maximum here, and then decreasing to a minimum here. And we end somewhere around there. You may notice, whereas our position versus time graph was a sine function, our velocity versus time graph is a cosine function here. Finally, we have our acceleration versus time. Remember, acceleration versus time is the slope of velocity versus time. So, well, our velocity versus time starts at about 0 in terms of the slope, and then it starts going in the negative direction, all the way to about here where it hits a maximum. Then it starts going down to 0 around there. Hits another maximum here, about 0 around there. Hits another maximum, about 0 at the end. Okay, so where our position versus time graph was sine, velocity versus time was cosine, acceleration versus time is a negative sine graph. Now, what I really want to point out are these key points lining up here and here, similarly as here and here. So check this out. When you have reached the farthest end, the most displaced that your pendulum is going to be, that is where you are going to have the minimum amount of velocity. You're going to have 0 velocity at that point. You're also going to have a maximum amount of acceleration, pulling it back towards its equilibrium. Then, when your pendulum's at the middle of its motion, the very center, it is at the highest speed. It is moving fastest when it is passing through the center of its motion. And it also has the smallest amount of acceleration. Okay? And then that pattern kind of keeps on going. Here we are at the other far end of our motion. We have 0 velocity and a high amount of acceleration. Here we are back at the center of our motion. We have a high amount of velocity and zero acceleration, and that pattern repeats over and over and over again. These key points are things that the AP test likes to ask you about a lot. They like focusing on the far ends of the motion and then the center point, because that's where we can do the most straightforward analysis in terms of understanding the motion of pendulum like this. So let's talk about a couple important vocab words that we're going to talk about a lot during this unit. The first one, well, the first two actually, we've already talked about in this class, but I want to review them so that we are all still on the same page. Period, for us, is going to mean the time it takes for one cycle of motion. So it is the time it takes for a pendulum to swing out and then back in. That would be the period for us. Okay? If we look back here at my position versus time graph, I'm going to mark out how long a period would be. It'll end right there. That is the length of our period because it has produced one full cycle of the motion. At that point right here, the motion is just going to repeat again. So that's our period. Then we have frequency. Frequency is the number of cycles in a second. It is a number of cycles in 1 second. Friendly reminder, unit for frequency is going to be hertz, okay? And frequency and period, they have a relationship. They're actually inversely related, meaning that if I needed to figure out the frequency, I could just take 1 over the period to solve for that. Or if I had the frequency, I could take 1, or if I was looking for the period, I could take 1 over the frequency to solve for it, okay? Finally, we have our actual new vocab word here. That's the amplitude. We're going to say that is the max distance from equilibrium. The max distance from equilibrium. Okay? So looking back here, our amplitude would be measured at this point here. It would be this distance there. It could also be measured here. It would be this distance here. This, that is not an amplitude. Amplitude is a distance. It's a measurement of distance. So whatever number this is that I just crossed off, it can tell us something. It tells us the maximum amount of velocity at that point, but we would not consider it an amplitude. Amplitude is exclusively a measurement of distance. It's a physical measurement of distance in the world. Okay? So there you go. Those are 3 vocab words that are going to be very important for the rest of this unit. Let's move on. Here I have drawn out 6 different pictures. On the top, we have a pendulum swinging back and forth. Here at A, it has been pulled up to this position and it is then released. It swings to B. At B, it is at the lowest position it will reach. And then at C, it has reached the highest on the right-hand side. It has reached the same height that it started at back over here. And so what this pendulum is going to do is it's going to start here and then swing out and then swing back in and swing out and just keep going back and forth and back and forth and back and forth. Then on this bottom set of pictures, we have a spring attached to, or sorry, a block attached to a spring attached to a wall on a frictionless surface. Here at point A, the spring has been extended with the block attached. It is then released. The spring pulls the block back to point B. Point B is the equilibrium position for the spring, meaning that at this point right here, that spring is not extended at all. There is no extension, there is no compression in the spring. Okay? And then the block moves past that all the way to C where it is compressed, at which point the spring starts pushing it back towards B and then moves past through that all the way to A. And it bounces back and forth forever. All right? So why did I draw these out? Well, what we are going to do next is we are going to look at the amount of energy and the type of energy in the system at each of those points. Okay? So let's go back here. Let's start with point A for the pendulum up in the top left. It is not moving. There is no spring involved. Therefore, and it is also being held above the ground. So therefore, I'm going to say that it has exclusively gravitational potential energy and zero kinetic energy. Okay? So we release it from point A and it moves to point B. At point B, let's just say it's on the ground. It's not actually touching the ground, like it's not rubbing on the ground or anything, but we're going to call our ground at that point because then we can say that we will have zero potential energy because we're on ground, so that all that potential energy back from A converted to kinetic energy at B. Then we move past that to C. Well, at C, it's no longer moving, and it's reached a new height. It's actually reached the same exact height it was at A, so our kinetic energy will be zero, and we will have a large amount of gravitational potential equal to what we had at the beginning. All right? Then if we look down at the bottom set of pictures back at our spring, it'll follow a very similar pattern. We start with a bunch of spring potential and zero kinetic. It's not moving at A, and it is just stretched out. Then you release it from A. It passes through its equilibrium point. Well, at its equilibrium, it has no spring potential because the spring isn't stretched at all. And also, all of that potential energy has converted to kinetic energy. Okay? Finally, we move past B and all the way to C. Well, at C, it is no longer moving, so it has no kinetic energy. It is all converted to potential spring energy. All right? So these are the basic energy graphs for a simple pendulum moving back and forth and a simple spring block system moving back and forth. Okay. Sweet, we're doing well so far. A couple things that I want to point out. Like I said, the AP really likes focusing on these like extreme points, meaning all the way at the end of the motion and all the way in the middle of the motion. A couple key facts that we want to discuss that I want to highlight for you guys. Here at point C over here, and this will also be true at point A, but we are going to have a couple maximums. We're going to have max acceleration at that point, right? We're going to have the most amount of acceleration. We are also going to have the least amount of velocity at that point. We are also going to have the maximum amount of force as well. So maximum, because we have the most amount of force at that point, we have the most amount of acceleration. So that's what's going on there at C. And again, that is true for point A as well, and that is also true for point A and C on our springs as well. Here at point B, we are going to have a maximum velocity at this point. Maximum velocity, and we'll have a minimum acceleration and a minimum amount of force. Okay? Those are important. I just feel like the AP really likes harping on those points right there, so I wanted to highlight them for you. All right, moving forward. Hey, we got some equations to talk about. These are the two main equations that we care about in this unit. The first one up here is the period of a pendulum. It's the equation for a period of a pendulum. So that period is equal to 2 pi times the square root of the length of that pendulum divided by the acceleration due to gravity. Okay? So that length up there at the top, that value is an L. It's just a fancy L because that's how we draw it in physics. And this is going to be how we can calculate the period of a pendulum swinging back and forth. Then on the bottom here, we have the same thing, period of a oscillating spring system this time, all right? Kind of similar structure. The period is equal to 2 pi times the square root of, well, instead of L over G this time, we're going to have M, so the mass at the end of the spring, divided by the spring constant. Okay, the spring constant, meaning the strength of the spring in the system. All right. Finally, we have this equation here. This equation is not technically in the curriculum for AP Physics 1, but for some reason, they put it on the equation sheet. Don't know why. But I always get nervous that the AP is going to ask you a question using this equation, and I just want to make sure you guys at least have it in your brain just in case. So this equation, it's designed to tell us the position of an oscillating object, okay? So we can solve for that position by taking the amplitude of the object, so that's the maximum distance that the object will ever reach, times the cosine of 2 pi times frequency times the time, meaning the time at which you're looking for the position of the object, okay? I don't need to spend a lot of time talking about this because I don't think you're ever going to need this equation, but I just want you to put it in your brain, have it in your back pocket, just in super case you get asked about it on the AP exam, all right? So there you go. Let's do an example problem. Let's say I got a simple pendulum and I've brought it to a new planet. I'm actually going to use this pendulum to test what is the acceleration due to gravity on that planet. I want to figure out what the G value on that planet is. So I've got this pendulum. It has a length of 37.1 centimeters and a frequency of 1.27 hertz. So I've measured that frequency somehow. And now what I'm going to do is I'm going to take that and figure out that G value, that acceleration due to gravity. I start with the period of a pendulum, this new equation that we just learned. Looks like that. Okay, so here's the issue though. We don't know period, we know length, but we don't know G. So that's two variables that we don't know. But we do know the frequency. And what we learned just a few minutes ago is that the period can be found by taking the inverse of the frequency. So I can just take 1 over 1.27 and I figure out that that is 0.787 seconds. Okay, so now I have enough. Now I know the period and I know L, so I can solve for G. Let's do this. Period is 0.787 equals 2 pi. Square root of 37 centimeters is 0.371 meters divided by G is what we're solving for. Okay? So I'm going to take my math real slow here. I'm just going to take 0.787 and divide by 2 pi here. I'll get 0.125 equals square root of 0.371 over G. I will then, I'll square both sides in order to solve this. So I'll take 0.125, square that. I got 0.0157 equals 0.371 over G. I'm going to multiply G over there. I'm going to divide this side by that. And I'm going to end up with the fact that G equals, let's see, G I solved here to be 23.59 meters per second. So that is acceleration due to gravity on this new planet. I think that's something like the acceleration due to gravity on Jupiter. It would probably be very hard for you to stand up on this planet because that's a lot of gravity. But luckily, this is a fake problem. So there you go. That, I believe, wraps up our notes on simple harmonic motion. I hope this video was helpful for you. All right, see you later.